Welcome to our exploration of earthquakes, one of nature's most dramatic and unpredictable forces. Earthquakes have fascinated and frightened people for centuries, shaping landscapes and societies alike. In this video, we'll uncover what earthquakes are, how they happen, and why understanding them is crucial for our safety and scientific knowledge. We'll also look at the myths and science behind these powerful events, and how modern technology helps us detect and respond to them. Let's begin our journey into the world of earthquakes and discover the secrets beneath our feet. Why do we dedicate so much effort to studying earthquakes? It's not just curiosity. Earthquakes can have devastating effects on communities, infrastructure, and lives. By understanding how and where earthquakes occur, scientists can help assess risks, improve building codes, and develop early warning systems. While we can't predict the exact time and place of the next big quake, our growing knowledge helps us prepare and respond more effectively. Studying earthquakes is about making our world safer and more resilient in the face of natural hazards. Throughout history, people have tried to explain earthquakes through myths and legends. In Japanese folklore, a giant catfish living beneath the earth is believed to cause earthquakes when it thrashes about. In Scandinavian mythology, the god Loki is said to be tied to a rock underground, and his struggles shake the earth. These stories reflect humanity's need to make sense of powerful natural events. Today, science offers us a clearer understanding, but these legends remind us of the awe and fear earthquakes have inspired for generations. In Scandinavia, earthquakes were once explained by the story of Loki, a mischievous god tied to a rock as punishment for his deeds. Whenever Loki twisted and struggled underground, people believed the earth would shake. These tales helped ancient communities cope with the fear and unpredictability of earthquakes, offering a sense of explanation and control. While we now understand the scientific causes, these legends are a fascinating part of cultural history and show how deeply earthquakes have impacted human imagination. The story of Loki's punishment is so central to Scandinavian folklore that it's often retold in different ways. Sometimes, Loki is said to be tied underground for killing his brother Thor, and his movements are blamed for the trembling earth. These stories highlight how people across the world have sought to explain the mysterious forces beneath their feet. Today, we know that earthquakes have natural causes, but these myths remain a testament to human creativity and the desire to understand our environment. What exactly is an earthquake? At its core, an earthquake is the shaking of the ground caused by the sudden release of energy within the earth. This energy is released in several forms: seismic waves which travel through the earth, displacement along faults where rocks move past each other, and heat. Earthquakes can range from tiny tremors barely felt to massive events that reshape landscapes. Understanding these basics is the first step in grasping the science behind earthquakes. Earthquakes happen all the time, all around the world. For example, in just the last 30 days, there have been numerous earthquakes above magnitude 1.5. These events are tracked and mapped by scientists, helping us understand where earthquakes are most likely to occur. By studying recent activity, we can see patterns and identify areas of higher risk, which is essential for preparedness and safety planning. Looking at earthquake data over the past year reveals even more about their distribution and frequency. Scientists use this information to monitor trends and assess long-term risks. By mapping out where earthquakes have occurred, we gain valuable insights into the behavior of the Earth's crust and the forces at work beneath us. This data-driven approach is key to improving our understanding and response to seismic hazards. When an earthquake occurs, two important terms come into play: the focus and the epicenter. The focus is the point inside the earth where the earthquake starts, while the epicenter is the point directly above it on the surface. Understanding these locations helps scientists determine where the most intense shaking will be felt and how the energy spreads outward. This knowledge is crucial for emergency response and public safety. Seismology is the scientific study of earthquakes and the seismic waves they produce. The word comes from the Greek seismos, meaning shaking, and ology, meaning study. Seismologists use a variety of tools and techniques to analyze earthquakes, understand their causes, and predict their effects. This field is at the heart of earthquake research and plays a vital role in keeping communities informed and prepared. Earthquakes are caused by the buildup and sudden release of stress within the Earth's crust. This process involves both elastic and brittle deformation, but not usually plastic deformation. Over time, stress accumulates along faults, cracks in the Earth's surface, until it overcomes the friction holding the rocks together. When this happens, the stored energy is released as an earthquake, shaking the ground and sometimes causing significant damage. One of the main explanations for how earthquakes occur is the elastic rebound theory. Imagine a fault, a crack in the Earth's crust locked by friction. As stress builds up, the rocks on either side deform elastically like a stretched spring. Eventually, the stress becomes too great and the rocks snap back to their original shape, releasing energy as an earthquake. This process explains why earthquakes can be so sudden and powerful. Stress continues to build along a locked fault, the rocks on either side become increasingly deformed. This elastic deformation stores potential energy much like a compressed spring. The longer the fault remains locked, the more energy is stored, setting the stage for a potentially larger earthquake when the fault finally slips. Understanding this process helps scientists estimate earthquake risks in different regions. When the stress finally overcomes friction, the earthquake begins at the focus, deep underground. The epicenter is the point directly above this on the surface. From the focus, seismic waves radiate outward, shaking the ground as they travel. Knowing where the focus and epicenter are located helps emergency services respond quickly and effectively to earthquake events. After an earthquake, the rocks on either side of the fault have moved past each other, a process called slip. The amount of slip can vary, with larger earthquakes generally involving more movement. Sometimes the slip isn't visible at the surface, but the energy release can still be immense. Once the fault relocks, the cycle of stress buildup begins again, setting the stage for future earthquakes. Elastic rebound theory applies to all types of faults, whether they're strike-slip, normal, or reverse faults. The orientation of the fault may change, but the basic process of stress buildup and sudden release remains the same. This universality helps scientists apply their knowledge to different geological settings around the world, improving earthquake risk assessments everywhere. Vancouver sits above a subduction zone, making it a region of significant earthquake risk. Even though it hasn't experienced a major earthquake in over 300 years, stress continues to build in the rocks below. This means the area could be at risk for a very large earthquake in the future. Understanding local geology and tectonic settings is essential for preparing communities and reducing potential damage. Earthquakes can happen almost anywhere, but most occur near the boundaries of tectonic plates. In fact, more than 90% of all earthquakes strong enough to be felt happen along these boundaries. The famous Ring of Fire around the Pacific Ocean is especially active. However, about 10% of earthquakes occur within plate interiors, so no place is completely safe from seismic activity. By observing global earthquake patterns, scientists have found that the kind, size, and frequency of earthquakes depend on the type of tectonic boundary. For example, subduction zones tend to produce larger, more powerful earthquakes, while transform boundaries often generate frequent, smaller quakes. This knowledge helps guide building codes and disaster preparedness in different regions. Seismic waves are the energy waves generated by the sudden movement of rocks during an earthquake. These waves travel through the earth and are responsible for the shaking we feel. There are two main types: body waves, which move through the interior of the earth, and surface waves, which travel along the earth's surface. Understanding these waves is key to interpreting earthquake data and assessing their impact. Body waves are divided into two types, starting with P waves or primary waves. These are the fastest seismic waves, traveling at speeds up to 13 kilometers per second in the mantle. P waves move particles in the same direction as the wave travels, and they can pass through both solids and fluids. Because they arrive first, P waves are crucial for early earthquake detection and warning systems. Second type of body wave is the S wave or secondary wave. S waves travel more slowly than P waves and move particles perpendicular to the direction of wave travel. Unlike P waves, S waves can only move through solids, not fluids. Their unique motion and speed help scientists determine the structure of the Earth's interior and locate earthquake epicenters. Surface waves travel along the boundaries between different materials such as the ground and air. Rayleigh waves, a type of surface wave, move in both vertical and horizontal directions, similar to ocean waves. These waves are slower than body waves but often cause the most damage during an earthquake because of their rolling motion and strong ground shaking. Another type of surface wave is the love wave, which moves the ground horizontally, perpendicular to the direction of wave travel. Love waves are particularly destructive because they cause intense side-to-side shaking at the surface. Their unique motion makes them a significant factor in earthquake damage, especially to buildings and infrastructure. Surface waves, including both Rayleigh and love waves, are responsible for the most noticeable and damaging effects of earthquakes. Their slower speed means they arrive after body waves, but their energy is concentrated at the surface, where people and structures are most vulnerable. Understanding how these waves move helps engineers design safer buildings and infrastructure. When an earthquake occurs, the order in which seismic waves arrive at a distant location is important for both detection and safety. P waves arrive first, followed by S waves, and finally the slower, more destructive surface waves. This sequence allows early warning systems to detect the initial P waves and provide precious seconds of warning before the strongest shaking begins. Seismographs are the primary tools used to detect and record earthquakes. These instruments work by suspending a mass on a spring. When the ground shakes, the mass remains still while the frame moves, causing a pen to record the motion. This simple yet effective design allows scientists to capture the details of seismic waves and analyze earthquake events in real time. Canada, a network of about 200 seismographs, monitors earthquake activity across the country, with around 30 located in southern British Columbia. These networks provide valuable data for scientists and emergency planners, helping to detect earthquakes quickly and accurately. The information gathered is essential for issuing warnings and guiding disaster response efforts. Earthquake early warning systems rely on the fact that P waves travel faster than the more damaging S waves and surface waves. By detecting the initial P waves, these systems can send alerts before the strongest shaking arrives, giving people valuable time to take cover. Early warning is a powerful tool for reducing injuries and saving lives during major earthquakes. Let's break down how early warning systems operate. When an earthquake occurs, P waves are detected first because they travel at about twice the speed of other seismic waves. For example, if a subduction zone earthquake occurs 300 kilometers away, P waves might arrive in 60 seconds, while surface waves take 100 seconds. This 40-second window can be critical for taking protective actions, such as dropping to the ground or stopping train. Canada has developed its own earthquake early warning system, designed to detect seismic waves and issue alerts as quickly as possible. This system is part of a broader effort to improve public safety and disaster response. By leveraging advanced technology and a network of seismographs, Canada aims to provide timely warnings and reduce the impact of future earthquakes. Locate an earthquake's epicenter. Scientists use the arrival times of different seismic waves at various seismograph stations. Because P waves, S waves, and surface waves travel at different speeds, the time gaps between their arrivals can be measured and used to calculate the distance to the epicenter. This process is fundamental to earthquake monitoring and response. Further, a seismograph is from the epicenter, the longer the time difference between the arrival of P waves and S waves. By comparing these time differences at multiple stations, scientists can pinpoint the location of the earthquake. This method is both precise and reliable, forming the backbone of modern earthquake detection systems. With just one seismograph, scientists can estimate how far away the earthquake occurred but not the direction. Adding a second station narrows it down to two possible points. With three or more stations, the exact location can be determined by triangulation, where the circles drawn from each station's data intersect. This technique is essential for rapid and accurate earthquake response. Earthquakes are measured in two main ways: magnitude and intensity. Magnitude refers to the amount of energy released, while intensity describes the effects and damage experienced at the surface. Both are important for understanding the impact of an earthquake and planning for future events. Different scales are used for each, and local geology can influence the observed intensity. Magnitude is a measure of the energy released at the source of the earthquake, often calculated using the moment magnitude scale. Intensity, on the other hand, is a measure of the earthquake's effects on people, buildings, and the landscape, commonly assessed using the modified Mercalli scale. Both measures are influenced by local geology, which can amplify or dampen the shaking. Richter scale was once the most widely used method for measuring earthquake magnitude. Developed in the 1930s, it calculates magnitude based on the amplitude of seismic waves recorded by seismographs. While still referenced today, it has largely been replaced by more modern and accurate scales, such as the moment magnitude scale. Moment magnitude scale is now the standard for measuring earthquake magnitude. It provides a more accurate estimate of the total energy released, especially for large earthquakes. This scale takes into account the area of the fault that slipped, the amount of slip, and the properties of the rocks involved. It's a crucial tool for scientists and emergency planners worldwide. Modified Mercalli scale measures earthquake intensity based on observed effects and damage. Unlike magnitude, which is a single value for each earthquake, intensity can vary widely depending on location, building types, and local geology. This scale helps emergency responders assess the impact and prioritize aid where it's needed most. Local geology plays a major role in how strongly an earthquake is felt. Soft soils can amplify shaking, while solid bedrock tends to dampen it. This means that two places the same distance from the epicenter can experience very different levels of damage. Understanding local conditions is essential for designing earthquake-resistant structures and planning emergency responses. Being prepared for earthquakes is everyone's responsibility. This includes having emergency kits, knowing safe spots in your home or workplace, and practicing earthquake drills. Communities can also invest in early warning systems and enforce building codes designed to withstand seismic shaking. Preparation saves lives and reduces the impact of these natural disasters. During an earthquake, the best advice is to drop, cover, and hold on. Move away from windows and heavy objects and protect your head and neck. If you're outside, stay away from buildings and power lines. Practicing these steps regularly can make a big difference when a real earthquake strikes, helping you stay calm and safe. Modern technology has revolutionized earthquake detection and response. From advanced seismographs to real-time data sharing and early warning apps, we have more tools than ever to monitor seismic activity and alert people to danger. Continued investment in technology will help us stay ahead of future earthquakes and minimize their impact. Earthquakes have shaped human history, influencing where we build, how we live, and even our myths and stories. By learning from past events and applying scientific knowledge, we can build safer communities and reduce the risks posed by future earthquakes. Our relationship with earthquakes is ongoing, and staying informed is the key to resilience. Earthquakes are a natural part of our planet's dynamic system. While we can't prevent them, we can understand, prepare for, and respond to them more effectively. By combining scientific research, technology, and community action, we can reduce the risks and build a safer future. Thank you for joining us on this journey through the science and stories of earthquakes. Stay safe, stay informed, and remember, knowledge is our best defense against the unexpected.